In this video, we are going to discuss the interest rate background necessary for your derivatives course. So first, we're going to talk about discount factors. Interest rates are all about present value, right? The present value of a cash flow in the future is its value today. And when discussing interest rates, one is really talking about present value. Now, the interest rate is a quick and pretty well understood way of describing present value. And finally, I should say that generally, the present value of a cash flow in the future is less than the value of the cash flow itself in the future, which of course is not true everywhere. We have seen over the last 5 to 10 years lots and lots of places that have negative interest rates, in which case the present value of a cash flow in the future is larger than that cash flow as opposed to smaller than. But for the purposes of this course, we're going to worry about interest rates which are positive and thus our normal relationships between present value and cash flows hold. Now, discount factors is a new concept for most of you. So the discount factor is the present value of a dollar paid at some time in the future. And if we know, for example, we're going to be paid N dollars at time t in the future, then the present value of N dollars is N times the discount factor at time t. Alternatively, if we invest P dollars today, then at time t in the future it is worth future value equals P divided by discount factor. Now, this is just a convenience. And the nice thing about discount factors is when we want to calculate present value, we simply multiply by the discount factor. If we were doing that same calculation and we knew an interest rate, it would be a little more involved. Now, discount factors are a construction, as in nobody quotes discount factors in the market. So discount factors are construction to make the math convenient, but no one's ever going to quote these things, so we're going to have to convert between interest rates and discount factors and so on. Now, if we have an annualized interest rate, R, for time t, we can find the discount factor as discount factor, time t, equals 1 over 1 plus R to the power t. So for example, if we know the annualized interest rate for 6 months is 4%, the discount factor for 6 months is given by discount factor equals 1 divided by 1 plus 4% to the power of half, or 0.980581. If we know a discount factor, say 0.98 for 1 year, we can find the annualized interest rate by inverting this formula. We do a little bit of work, and we can find R equals 2.0408. Now, we could have seen, let's look at the second calculation for a second. This is a discount factor for a year. And we can see to get a dollar, to end up with a dollar in a year, we have to earn about 2 cents. 2 cents on a dollar is about 2%. Or 2 cents on a dollar is exactly 2%. So the interest rate is about 2%, 2.0408 to be exact. Okay, next we're going to talk about continuously compounded interest rates. And again, I'm assuming you've seen these before, but I just want to remind you. So we'll often use continuously compounded interest rates, and sometimes we'll call those zero rates. So these are mathematically nicer than other kinds of rates. And the present value, future value formula is present value equals future value, or the cash flow itself, e to the minus RT, or future value is present value, the amount we invest, e to the RT. So a lot of you probably don't love seeing that e to the RT, but again, the e to the RT, the exponential function, and the natural log function turn out to be mathematically really nice and convenient to work with. And so there are some properties of continuously compounded interest rates, which are only sort of true for other interest rates. And so we will often, when not working in the market, when not quoting things in the market, we'll often use continuously compounded interest rates rather than other kinds of rates. So we can calculate a discount factor from a continuously compounded rate. Remember, the discount factor is the present value of a dollar. So the discount factor for time t given by the continuously compounded rate R is discount factor equals e to the minus RT. Pretty straightforward formula. Okay, let's do an example. What is the discount factor for 6 months when the continuously compounded interest rate is 4%? So again, the discount factor formula is discount factor equals e to the minus RT, or discount factor equals e to the minus, looks like I'm missing a minus sign in there, so that should be e to the minus 4% times a half, or 0.980199. What is a continuously compounded interest rate for 2 years if the discount factor is 0.947642? Well, e to the minus 2, number of years, r, equals 0.947642. And here's where natural log comes in handy. Take the natural log of both sides. Negative 2r equals natural log of 0.947642. And we can solve for r, and we get 2.6889%. Again, mathematically, e to the power and natural log, those are inverse functions. It makes our lives a lot easier and more convenient to work in continuously compounded rates rather than any other kind of interest rate. Next, we want to discuss forward rates. So this is probably a new concept for many of you. So let's take a look at what we're talking about. Let's say we want to invest until sometime T1, and we have a choice of investments that can be locked in today. So the first investment is investing at some rate, R1 we'll call this, until T1. So we're basically going to take our money and we're going to invest at a known interest rate until time T1. The alternative would be to invest at R0 until sometime before T1 and then reinvest the money at some other rate, we'll call that R01, between T0 and T1. The forward rate is the rate, R01, that makes us indifferent between these two choices. Okay, so what do we mean here? We mean that basically we're going to set up investments today, and version 1 of the investment is invest all of our money until time T1. Version 2 of the investment is to invest all of our money until time T0, and then take whatever money that is and invest it until time T1. And importantly, we're deciding these investments, we're agreeing these investments today. So we're not waiting until time T0 to reinvest. We're basically saying, let's go to the bank and let's invest money, but we're not going to invest money today. We'd like to invest money starting in, let's say, 3 months and going for another 3 months. Now, the forward rate is the rate that makes us indifferent between these two choices. Now, let me draw a picture, and it's probably a little easier to think about. So let's look at the bottom half of this picture. Our investments go to time T1 always. So we have a timeline. We have today, we have T0, and we have T1. The bottom part of this picture is investing our money at some rate until time T1. So that's the bottom half. We take our money, we lock it away, we don't get it back until time T1. The top part is we're going to invest our money from today until time T0 at some rate, R0, we can find that rate in the market, and then we're going to we touch our money for just a second, and then we invest it at R01 between T0 and T1. And the forward rate is the rate that we agree today that makes us indifferent to which of these two things we do. And of course, we should be indifferent to which of these two things we do because we basically receive back some money at time T0, the money we invested plus the interest, and then we immediately turn around and invest it again, and we don't have any choice because we agreed to deposit it or lend it to somebody between T0 and T1 at some rate up front. So basically we get to touch our money, but we don't really get to touch our money. We have to immediately reinvest it. So there should be a rate which makes us indifferent to which of these things we do. And that rate is called the forward rate. Now we can also draw this picture in terms of discount factors, and I'm going to do that here, and it looks pretty much the same, except the arrows go the other direction. But let me describe what's going on with discount factors. So we're going to take the present value. Discount factors are present value, right? So discount factor 1 is the present value of $1 paid at time T1. Discount factor 0 is the present value of $1 paid at T0, and we're going to call discount factor 01 to be the future value at time T0 of $1 paid at time T1. And in words, that DF01 is the forward discount factor if we're indifferent to which we do, right? Discount factor, the present value of $1 paid at time T1, present value as of today, that's discount factor 1, should be the same as the future value at T0 for $1 paid at T1, discounted back to today. Now mathematically, we have a really nice formula. Discount factor 1 equals discount factor 0 times discount factor 0,1. Basically saying that forward discount factor, DF01, makes us indifferent to which investment we have. So, this is our key formula. Again, in rates, it's going to be messy because you've got to deal with interest rates. Discount factors, it's really, really straightforward. DF1 equals present value of $1. We're indifferent, as long as we use the forward discount factor, we're indifferent to whether we discount all at once from T1 back to today, or we stop somewhere in the middle and then continue. Discount factor 1 equals discount factor 0 times discount factor 0,1. So that's forward discount factors. Forward interest rates, if we have the relationship between discount factors, then we can find forward interest rates. And these are the rates that make the discount factor equation hold. Discount factor 1 equals discount factor 0 times discount factor 0,1. The forward interest rate is the rate that one would agree today, assuming that one can borrow or lend at known rates R0 and R1. The forward interest rates is not the same, this is an important thing, as our expected interest rate. The forward interest rate is the rate we can agree today so that there's no arbitrage in the market. There's no free money to be made in the market. Now, for those who have studied some interest rate theory, the forward interest rate is the expected interest rate under the expectations theory of interest rates. But the expectations theory of interest rates has some serious flaws in it, and one generally would believe or would expect that interest rates might be higher or lower than this rate. So the forward rate doesn't tell us, the forward interest rate doesn't tell us what we think the rate's going to be in the future, right? When we get to time T0, what interest rate is going to be available then? The forward interest rate is the rate available today. Okay. For continuously compounded interest rates, the forward rate is really simple to calculate. And it can be calculated using this formula, R01 equals R1T1 minus R0T0 over T1 minus T0. So this is a really nice formula, and this formula just drops out of the discount factor formula and the discount factor for continuously compounded interest rate formula. I'm not going to do that derivation here. You can find the derivation in the notes if you want. But again, pretty straightforward application of two formulas, forward discount factor formula and the discount factors for continuously compounded rates. And you basically take a natural log and away you go, and out drops this formula. Now this is a really nice formula. It's pretty straightforward to do calculations with. It is not true for any other kind of interest rate. It is close to true for rates as long as they've been annualized, but it's not true for any other kind of interest rate. And this is one of the reasons why, for continuously compounded rates, it's convenient to work. Okay, let's do an example. Continuously compounded zero rate for 6 months is 3%. Continuously compounded zero rate for 12 months is 3.5%. What is the continuously compounded forward rate from 6 to 12 months? Plug it into our formula. If we don't remember the formula, we can always go back to first principles, work with discount factors. Remember the formula for discount factor equals e to the minus RT and go from there. But we plug in our formula and we end up with 3.5 times 1 minus 3 times a half divided by 1 minus a half, which is 4%. And let's just think about this in words. We're earning 3% over the first 6 months, and if we invested for 12 months, we're earning 3.5%. Well, over the first 6 months, we're earning 0.5% too little, right? Because over 12 months, we should be earning 3.5. That means that over the last 6 months, from 6 to 12, we have to earn 0.5% more in order to average out to 3.5. Well, 0.5% more than 3.5 is 4. That's our forward interest rate. Let's do one other example. Continuously compounded zero rate to lend and borrow for 3 months is 3%. The continuously compounded forward rate from 3 to 9 months is 2.75. What is the continuously compounded zero rate for 9 months? Well, same formula, 2.75, that's the 3 to 9 month rate, is equal to the 9 month rate times 9 minus the 3 month rate times 3 divided by 9 minus 3. Now you notice I've just used months instead of years. I could rewrite this, and instead of using 9, I could put 0.75. Instead of using 3, I could use 0.25. The math all turns out to be exactly the same. We can use days in this formula, we can use years in this formula, we can use months in this formula. It doesn't matter as long as we're consistent. And we end up with 16.5. Multiply all this out. 16.5 equals R9 times 9 minus 9%. And we solve for R9 is 2.83%. So those are forward rates. Again, key concept, we will use this over and over again, especially when we're talking about interest rate derivatives. All right, quotations. And I'm sorry, this is bouncing around a little bit, but this is how it works. These are the things you need to know. Interest rate quotations. So you're a customer of the bank. You walk up to the teller, you ask to deposit $1 million for 6 months. So well done, you've got $1 million to deposit. Not so well done, what are you doing depositing $1 million in your bank? But whatever. You've got $1 million to deposit for 6 months. The teller tells you, hey, you're going to earn 3% interest. A very natural question would be, at the end of 6 months, how much interest will I earn? How much money in dollars and cents do I receive? Right? That's a very reasonable question for you. If you're depositing $1 million, you want the answer. Now, give or take, 3% over a year is $30,000 on $1 million. So 3% annualized, $1 million deposit, that's $30,000. So for 6 months, it should be about $15,000. But of course, you've got $1 million in your pocket. You want to know precisely how much you're going to earn. Now, the 3% is imprecise, right? The 3%, if it represents an annualized interest rate, you're going to earn $14,889.16. It's $1 million times 1.03 to the 0.5, that's that future value formula, minus 1, because we have to figure out just the interest, and we end up with 14,889.16. If it were a continuously compounded interest rate, then you'd earn $15,113.06, a different amount. The bank, when it tells you the interest rate, is telling you something precise. It should be telling you precisely how much you earn. Now, no matter how the bank quotes that interest rate, it's going to pay you a certain amount of money, right? They're not going to give you the choice to choose which interest rate. You are always going to be given a certain amount of money. The present value is always the same no matter how one quotes the interest rates, or alternatively, the future value is always the same. Now, imagine the bank chose to quote interest rates using continuously compounded. Okay, first off, how many customers of the bank are comfortable raising a number to a power? Right? E to the RT. Second, how many customers of the bank are comfortable with E? How many people in this class are comfortable with E? And how many bank tellers are comfortable teaching Algebra 2 to their clients? Right? If the bank quotes interest rates using E to the RT, continuously compounded rate, a fair question when you ask the bank, how much interest will I earn? And the bank tells you, let's go back to the number, 15,113.06. A very reasonable question is, how did you calculate 15,113.06? And when the bank says, oh, I took $1 million, e to the 0.03 times 0.5 minus 1, a fair question is, what the heck is e? If I'm a bank teller, I don't want to have that conversation. That is a bad conversation, right? I'm pretty comfortable. I know what E is. Hopefully the bank teller knows what E is. But explaining to a customer what E is when the customer doesn't know what E is isn't going to go well, which actually means even if the interest being paid to the bank is that $15,000, the bank is not going to quote interest rates using continuously compounded rates. And this is true whether it's a bank teller or whether it's an investment bank telling its clients. And again, we would expect that the investment bank's clients who are trading interest rate derivatives are pretty sophisticated and know what E is. But we still don't quote interest rates that way. And part of the reason we don't quote interest rates that way is that the probability of making a mistake when you plug the numbers into your calculator is high. And I'd rather give you an easier formula that we can all agree and check very quickly and easily that we all got the right answer. So there are two conventions that will be used in interest rates and that are used in the investment banking world for interest rates all the time. Now, there are other ones out there, and we're not going to deal with them in this course. You've got all sorts of stuff that show up in bonds and whatever. We're going to use these two conventions. These are the ones that show up in the interest rate derivatives world most often. So these are called actual over 360 and actual over 365. These are used for quoting interest rates in short-term markets. Actual over 360 is used in Switzerland, Europe, and the United States. Actual over 365 is used in, say, the United Kingdom and Japan. And interest is calculated using the formula, the amount times the rate times days over the basis, where basis is either 360 or 365. So $1 million times the rate, 3%, times the number of days, 182, 181, depends on the 6-month period we're doing, divided by 360 or divided by 365. It's $1 million, so it would be 360. The 360 is a little weird, right? Because basically this looks like amount times rate times days over number of days in a year. 360 in the United States comes from the Treasury bill market. The Treasury bill market was created, I think, in the 1920s. And my guess as to why the United States chose to use 360 days in a year as opposed to 365 was that it was a little bit easier to work with on a slide rule or something like that. But anyways, in the 1920s, somebody decided that in the United States, Treasury bills, short-term interest rate bonds issued by the Treasury bills will be quoted on this actual over 360 basis. And that stuck, and now we live with it today. So in the United States, short-term interest rates in most markets are going to be quoted as actual over 360. Your bank, for example, agrees to pay you interest on a time deposit of $1 million at a rate of 3% for 30 days on, again, this is the wrong basis, but on an actual over 365 basis. The interest you earn is $1 million times 3% times 30 over 365, or $2,465.75. We can also, if we know a discount factor, find the rate. What is the fair actual over 365 interest rate for 90 days if the fair discount factor for 90 days is 0.998543? Discount factor is the present value of $1. If I know my interest rate, I do 1 over 1 plus R times days over 365 to find the discount factor. And I can plug everything into my formula, and I end up with R equals 0.5918 after doing a little bit of work to manipulate. Right? Take 1 over both sides, subtract 1, multiply by 365 over days. So that's how we manipulate interest rates. There are key formulas, and actually there are 4 formulas that I use all the time. So the first one is the discount factor for a continuously compounded rate. Discount factor equals E to the negative R days over 365. Actual over 360 rate, discount factor equals 1 over 1 plus R 360 times days over 360. And for an actual over 365 rate, pretty much the same formula. Discount factor equals 1 over 1 plus R 365 times days over 365. the key concept, the key thing to keep straight is that the discount factor is always the same, right? Present value of a dollar is always the same no matter how we quote the interest rate. So I can work from, if I know a continuously compounded rate, I can calculate the discount factor. If I know the discount factor, I can calculate an actual over 360 rate, and so on and so forth. If I know one kind of rate, I can calculate another. Now, the other formula, which is really important, is the forward rate formula, and that is R01 equals R1T1 minus R0T0 over T1 minus T0. So that's how we calculate forward rates, but that's only for continuously compounded rates. Those four formulas allow me to do all the manipulations I want to do for interest rates. So I need to know these formulas. Again, in my mind, there's really only three formulas here, right? The continuously compounded one for discount factors, the discount factor for a rate with a basis. Those two formulas are really the same. And then my forward continuously compounded rate calculator. So if I need to find a forward discount factor, what do? Take rates, convert to discount factors, either use df1 equals df0 times df01, which is the same as that continuously compounded rate formula. Okay, couple other points. Risk-free interest rates. Risk-free interest rates are going to be talked about a lot in the derivatives course, and they are a cornerstone of derivatives pricing. So when you go into derivatives pricing, one almost always starts to talk about risk-free interest rates. So risk-free interest rates are interest rates where one can borrow or lend at the same rate. One can borrow or lend in any size. So I can borrow $1 million at this rate, or I can borrow $1,000 at this rate. It doesn't matter. There are no transaction costs. No collateral is required. And there's no risk of default or non-performance for either borrowing or lending. So if I lend some money, I always get it back. If I borrow some money, I always pay it back. So these are risk-free interest rates, and this is not a legitimate market concept. There is no such thing as a risk-free interest rate. Now, the closest thing that appears to be default-free are U.S. Treasury bills, short-dated securities issued by the U.S. government. Now, in 2013, the U.S. thought about delaying payment on these, and so it might not be a great assumption that these are risk-free. But it's as good as we get, so generally we work with the assumption that Treasury bills or Treasury bonds are risk-free, and so those are risk-free rates. And we will do all of our derivatives math, or most of it, assuming that the risk-free rate does not exist. And when someone says risk-free, or when I say risk-free at some point in this course, think Treasury bill. The way the derivative market gets around this problem is through the use of collateral. So the presence of collateral allows one to use pretty much the same techniques for pricing derivatives that one uses when assuming that interest rates are risk-free. Now, the problem is, or the challenge is, we add a lot of complexity when we actually think about the actual mechanics of collateral. And there's no standardization of collateral agreements. The types of collateral that can be posted sometimes are different. And so the pricing of derivative contracts becomes really, really complex once you take into account collateral. I could probably teach an entire year's course on different ways to think about collateral and how it affects the pricing of derivatives. In the first instance, under certain pretty constrained assumptions, we can simply replace the interest rate, the risk-free interest rate, by the interest rate that's paid on the collateral. At which point, all of this complexity is not particularly useful in a first course on derivatives. So it's easier and probably pretty good to just assume that there exists a risk-free interest rate, there exists risk-free investments, interest rate investments, and work from there. And later bring into account collateral or add that complexity later.